DeepSeek R1 incentivizing reasoning capability in large language models via reinforcement learning, published by DeepSeek AI in January 2025. Here's the central question: can pure reinforcement learning teach an AI to reason? The answer is yes, and the results surpass human experts. Let's look at the three key contributions of this paper. First, they achieve reasoning through pure oral, with no human demonstrations. Second, they introduce a novel algorithm called GERPO that eliminates the need for a value model. And third, everything is open source weights, papers, and distilled models. Let's start with some background on how language models learn to reason. The dominant approach is chain of thought, prompting you ask the model to think step by step before giving a final answer. Leading models like GPT-4, Claude, and Gemini all use this technique. But how do you actually train a model to do this well? The traditional pipeline looks like this. You collect human-labeled reasoning data, then do supervised fine-tuning, then RALF, and finally you get a reasoning model. But this approach has three critical limitations. Its expensive human annotation costs scale linearly. Its biased human patterns constrain reasoning diversity. And its cap: the model can never exceed the annotator's own capabilities. DeepSeek's radical idea: skip supervised fine-tuning entirely and use pure reinforcement learning. But first, let's look at the foundation, the DeepSeek V3 base model, built on a mixture of experts architecture. The idea is simple but powerful. When a token comes in, a router decides which experts should process it. Not all experts are active at once. Each token only activates 8 out of 256 total experts. This gives us remarkable efficiency: 671 billion total parameters, but only 37 billion activated per token, trained on 14.8 trillion tokens. The architecture includes several key innovations: multi-head latent attention for efficient inference, multi-token prediction for faster decoding, and auxiliary loss-free load balancing to prevent expert collapse. They even used FP8 mixed precision training, cutting memory usage in half. And here's the kicker: the total pre-training cost was only $5.5 million. Compare that to GPT-4's estimated $100 million. Now for the breakthrough DeepSeek R10. The core idea is radical: train reasoning with RL only, 0 human reasoning demonstrations. You take the DeepSeek V3 base model, apply GERPO reinforcement learning with just an accuracy reward and a format reward, and out comes R10. The training uses a simple template. The model must put its reasoning inside think tags and its final answer inside answer tags. The result? 77.9% on AIM 2024, already competitive with OpenAI's O1 Mini at 63.6%. But R10 has known issues: poor readability, language mixing, and repetitive loops. These limitations motivated the full R1 pipeline. Let's dive into the core algorithm: Group Relative Policy Optimization, or GERPO. In standard PO, you need a policy model, a reference model, a reward model, and a separate value model of the same size to estimate advantages. That value model is extremely expensive. GERPO eliminates it entirely. Instead, for each question, it samples a group of multiple outputs, scores them all, and computes advantages relative to the group. No value model needed. The mathematics are elegant. The advantage for each output is simply how much better its reward is compared to the group mean, normalized by the group's standard deviation. Good outputs get positive advantages. Bad outputs get negative advantages. The full objective also includes a clipping mechanism and a Clay-L divergence penalty. This saves 50% of GPU memory. The reward system is surprisingly simple rules, not neural networks. There are two components. The accuracy reward checks if the answer is correct. Does the math answer match ground truth? Does the code pass all test cases? The format reward ensures the model uses the structured think and answer tags. Why avoid neural reward models? Because they're prone to reward hacking. The model finds shortcuts to maximize the reward without actually reasoning. An important design choice: DeepSeek uses outcome rewards, not process rewards. Process rewards judge each step but require expensive step-level labels. Outcome rewards only judge the final answer, cheap and scalable. Here's where things get truly remarkable. Something unexpected emerges during training. Look at these training curves. AIM accuracy climbs from 15.6% to 77.9%. Average response length grows dramatically. The model learns to think longer on harder problems. And then comes the aha moment. During training, an intermediate checkpoint spontaneously paused mid-reasoning and said, "Wait, I need to reconsider this." It then re-evaluated its approach and corrected itself. The model developed self-verification, reflection, backtracking, and alternative exploration all on its own. These behaviors were not programmed. They emerged purely from reinforcement learning. R10 showed great reasoning but poor readability and language mixing. The solution is a 4-stage training pipeline. Stage 1. Cold start SVT train on thousands of high-quality long chain of thought examples. Stage 2. Reasoning R large-scale reinforcement learning on math, code, science, and logic. Stage 3. Rejection sampling plus SVT generate and filter data, combining 600,000 reasoning samples with 200,000 general samples. Stage 4. Alignment RL optimize helpfulness, safety, and reasoning together. The result, DeepSeek R1 frontier reasoning, strong general capability, and human-aligned behavior. Let's look at the numbers. On AIM 2024, DeepSeek R1 scores 79.8% matching OpenAI's O1. Across all benchmarks, 97.3% on Math 500, 2029 Elo on Codeforces, 90.8% on Mamlu, 49.2% on SwiBench, and 71.5% on GPA Diamond. Even more impressive, R1E's reasoning can be distilled into smaller models. The distilled 30-B model scores 72.6% on AIM, beating O1 Mini.